We are at HIGREEW, a research center working on energy storage. We are coordinators and partners of the HIGREEW project, mainly working on the development of an aqueous organic electrolyte for redox flow batteries. From the development of active materials to the integration in the cell, our goal is to achieve greener batteries.
Everything starts with the design and synthesis of active materials which are based on earth-abundant elements. Hydrophilic groups are attached to the main structure to boost energy density. A structural characterization is also performed to assess both the identity and the purity of active materials. The main challenge on the discovery of these derivatives is, on the one hand, find molecules that behave well in battery, and on the other hand, that meet the needs of scalability, toxicity, and cost. For this reason, the simplicity of the synthetic route is crucial.
Chemical transformations allow us to modulate the properties of the material, such as the stability, solubility, and redox potential. A 3-electrode setup with a rotating electrode is used to study the behavior prior to the evaluation in the battery.
Critical aspect is the development of robust electrolyte which can withstand temperature changes while having good conductivity and moderate viscosity. We test electrolyte formulations with different conductive salts and concentration of active materials. In addition, we look for neutral pH-friendly electrolyte compatible with a variety of material for the cells.
It's really exciting to work in new technology to develop a sustainable solution for energy storage. Collaborating with EU partners has been very enriching to work together with a common purpose and getting the best of every partner and culture. We even succeed to create a researcher network beyond the project to put redox flow technology on the European political agenda.
HIGREEW project has offered us the chance to make a product from the lab to the final integration in an energy storage renewable plant. We have a wider view of the energy storage industry needs and are willing to put our knowledge to the service of society and the industry to contribute to a greener economy.
The HIGREEW project is a consortium of universities and business which pretends to design, develop and validate an efficient redox flow battery. Among the different tasks to reach this objective, University Autonomous of Madrid team has been in charge of selecting cost-effective commercial membranes for the future battery prototype. Membranes play an important role in the battery performance since it is the main responsible to avoid the cross-mixing of the redox-active material and represent a significant contribution to the resistance of the system. Therefore, it will determine the voltage efficiency and consequently the energy efficiency of the battery. In this regard, different membranes have been tested in order to select the best material which fulfill HIGREEW targets. Furthermore, different membrane modifications have been studied to enhance their performance.
So, the most challenging part has been the selection of the membrane. The market offers a wide variety of membranes, and each membrane presents different advantages and disadvantages, of course. These materials are defined by several physico-chemical parameters, and a deeply understanding and analysis of them has been the most challenging part. However, despite the difficulties found during the process, it let us reach interesting results that provides our personal satisfaction. Furthermore, keep in mind that we are working to ease the implementation of renewable energies into the electrical grid, which slows the climate change.
All the work developed in the HIGREEW project consolidates University Autonomous of Madrid team in redox flow battery field, especially regarding ion exchange membranes, and opens the door to face new further challenging projects and ideas. The expertise acquired during this project will be used in the development of new systems that may contribute positively to the energy storage field.
Working in a European project has been a very good opportunity to enrich the knowledge of all the team, especially for our PhD training. The interaction with the different partners around Europe let us be involved in other interesting research expertise through international collaborations, which is an outstanding opportunity to develop our professional careers and a fruitful experience for our specialized as well as personal skills. Besides, experts from business provide another enriching perspective focused on the feasibility of the research carried out in the laboratories to the final prototype for the global market.
Hello, we are here at LCPME, a CNRS laboratory in Nancy. We are working in HIGREEW with a colleague from Institut Jean Lamour, from Université de Lorraine. We are involved in HIGREEW on the optimization of the porous material for the HIGREEW electrolyte, and more specifically we are analyzing the reactivity in order to quantify, in order to optimize this reactivity for the better performance of the HIGREEW battery.
We work with carbon felt because it's the electrode used in the battery reactor. The activation of the surface is an important step before the application. It includes the modification of the surface of the carbon fibers in order to make it more hydrophilic, to increase the surface area of the material, and improve the affinity of the active species with the carbon. These improvements should be characterized, and in our work we used an approach with a scale analysis, centimeter square for the macrofelt, millimetric square with the microfiber, and micrometric square with the gel probe.
The most innovative approach is the gel microelectrode probe. We use it in the scanning gel electrochemical microscopy that we developed here in our lab. We have this tiny thin gel that contains the electrolyte attached to a microelectrode that we approach to the electrode surface. It allows to characterize by local electrochemistry individual fibers and different areas of these fibers directly on the carbon felt. In this way, we have insights on the impact of the treatment and the performance of the battery component at in situ and microscale.
After measurements, naturally the next step is to analyze the results. In this project, we have developed models for analyzing all the three scales to quantify the reaction kinetics at the electrode-electrolyte interface. This helped us choosing the right material and electrolyte in the project, and also will open the door for establishing a material database in future.
It was a really great experience to be working with HIGREEW partners for the development of this HIGREEW battery, especially because we could really see the link between the fundamental studies we have performed on the quantification of the electron transfer rate in this porous material and the consequence it can have on the performance of the battery.
Hello, we are here at New Technology Research Center, which belongs under West Bohemia University. We are partners of HIGREEW project, and the aim of this project is to develop redox flow batteries based on organic electrolytes, and these batteries should be environmentally friendly, should have high efficiency, very long lifetime, and of course need to be very cheap. The other partners within the project are developing certain components of the membranes, like electrolytes, carbon felt electrodes, or membranes. And our goal is to put all these components together, assemble a battery cell from it, and test it. And from the results which we will obtain from this measurement, give a feedback back to the partners if the battery is okay, which parameters are not okay, and which components should be optimized in which way. The other part of our research activity was about helping of the other partners with scale-up of the battery by usage of CFD modeling. In small single-cell batteries, there are a lot of aspects which are not very relevant, like pressure drop in the cell, flow distribution within the cell, or shunt currents. But when we try to scale up the battery, these aspects are really important and significantly influence the battery performance or lifetime. With usage of CFD modeling, we are able to visualize the flow within the battery. We are able to do it from macro to micro scale. From micro scale, we are able to measure with usage of microcomputed tomography the scans of carbon felt electrode. Afterwards, visualize the flow within the electrode. From the micro scale, we are also able to visualize the flow within the whole cell. And afterwards, these results are shared with other partners of the project and help them to design the battery. Work on this HIGREEW project was a very interesting experience for us, as we were right on the edge between the university partners and industrial partners. So we were able to observe the development of the battery from two different perspectives.
Pinflow Energy Storage is spun out from Czech universities, from New Technologies Research Center under the University of West Bohemia and from UCT Prague. We are fascinated about redox flow batteries. We believe that they are a reliable source of energy storage that can make the renewable energy available in the regime 24 hours, 7 days per week. Within HIGREEW, we are focused on scale-up of the technology from laboratory to industrial scale. It is difficult to conduct this scale-up process because everything that works at lab scale will be facing the issues in industrial scales. But our team is full of engineers and we are very focused to solve these challenges. Within the development of stack, we are playing with completely different chemistry. We need to solve different parameters. Now we are not working with identical chemicals as in vanadium-based systems, but we have different posylite and different negolite. We need to solve the viscosities, we need to solve ionic conductivities, and to develop a reliable leak-proof system. We are using CNC milling for manufacture of flow frames. The system is always tested at single-cell level and later at multi-cell level. In multi-cell systems, we are facing the issues related to shunt currents. We are trying to minimize shunt currents while we are preserving low pumping consumption. We are playing with completely new chemistries and we have verified that they are working even at kilowatt scale level. We are very glad that we had the opportunity to develop completely new stack for new chemistries.
Welcome to La Plana. Good morning. At the end, after several months, even years working with different projects, we are here for testing the HIGREEW battery. What are your first impression about the facility and the commissioning phase?
Okay. First, talking about the facility, I think you are proud. You should be proud of having this facility, to have the possibility to integrate and prove and validate different energy technology and different new energy generation sources as wind and solar. I think the work you are doing here in strategies and improving different integration of components, offering new ways of integrating, providing flexibility to the integration of renewables. I think it's a great opportunity having this facility. And for HIGREEW project, having the possibility of commissioning our development into this plant is a real opportunity to demonstrate that the outcome of this project has been a real product. We have integrated new redox technology based on organic electrolyte. And we are proud that this final product will open the door and the opportunity to new developments to really demonstrate that the first redox flow battery will have the gap in the deployment of new energy storage technologies for arbitrage and long-term energy storage. And hopefully, and we are very positive and optimistic, new electrolyte formulation based on organic redox flow battery will also open the door for more competitive or competitive LCOS for energy storage in Europe.
First of all, thank you so much for your kindly words. And for us, it's also a challenge to manage this kind of battery HIGREEW project. the end, we have to use this kind of batteries and also all kind of batteries. Lithium is very common for us. We are working in a plant for more than 5 years with lithium. Also with redoxflow batteries, with vanadium, but the new challenge with these batteries is amazing because we are not using vanadium, it's other kind of electrolyte. So we will see the results of the battery. Hopefully in the future we can use this kind of technology in any of the CMS.
Yeah.
Thank you, Javier, for visiting.
Thank you very much. I'm looking forward. Let's prove that we in Europe are able to deploy our own technology, and we set the basis for being less dependent on other raw materials that are scarce in Europe, and we set up the basis to be self-sufficient technologically and on the supply of the main components of these energy storage solutions. Yeah.